Hello and welcome. In this video, we're going to talk about the fundamental theorem of calculus and how that helps us evaluate a definite integral. So let's go ahead and get started. Before we get to what the fundamental theorem of calculus is, I encourage you to work through this warm-up here, questions 1 and 2. For number 1, you're just setting up the integral that would help you find that shaded area. You're not actually going to find the shaded area. And then for number 2, you're given the graph of the derivative and you're being asked some questions about that graph. So go ahead and pause the video and see which of those that you can work through on your own. And if you're having trouble, don't worry, we're going to go over them together in just a minute. Okay, hopefully you have had time to work through those problems. For number 1, if we're talking about the area under the curve, what we're really looking for is the integral from 0 to 2 of this function here. 2x squared minus 3x plus 2. Don't forget your dx. And as of right now, the only way that we know how to evaluate an integral that has bounds on it, or a definite integral, is to find the area under the curve or to approximate it using Riemann sums. And there has to be a better way to go about doing that, and that's sort of the purpose for this lesson. So we're going to leave it just as a setup integral. For question 2, the first thing we're asked is write what the integral from 0 to 5 of f prime of x dx means in words. So let's go ahead and do that. This integral from 0 to 5 of f prime of x dx is the area under the curve from x equals 0 to x equals 5. And since this is a linear graph, we could find that exact area by just finding the area of this rectangle, which has a height of 3 and a width of 5. So the area here is going to be equal to 15, again, because this is a line. So we could say the area, or the value of the integral, is equal to 15. Part B is asking us to write an equation for that function. So if we are looking at this function here, what is that function? That function is just f of x is going to equal 3. It's a horizontal line, the line y equals 3, or I'm sorry, f prime of x equals 3. That is the curve that we're looking at. Now, if we wanted to find what possibly f of x would be, we would just integrate that with respect to x. So we could say that f of x is 3x plus possibly some arbitrary constant. So we're going to hold a c value there. For question C, we are being told, well, what happens if we know enough to figure out what c is? We could say that when x is 1, f of x is 4. So 4 equals 3 times 1 plus c. So c is going to equal 1. So we could say that f of x is exactly the function 3x plus 1. So this graph is the antiderivative, or sorry, this graph is the derivative of the function that we just found here in part C. The area under that curve, the area under the graph of the derivative, formed with the x-axis from 0 to 5 was 15. What question D is asking us is, what happens if we actually find the values, what is f of 5 and f of 0, and subtract them? Because we just said that this is the area under the curve of f of x from 0 to 5. So could we look at that algebraically? Well, f of 5, if I plug 5 into this function here, 15 plus 1 is 16. F of 0, if I plug 0 and I get 1, 16 minus 1 is going to give us 15, and that is the same area that we originally found in part A. So is there a way that we could use this relationship between the function, or between the derivative and the antiderivative, and the numbers that are appearing on our bounds to calculate the area under the curve exactly without actually having to graph the function? And I sure hope so, because I know that most of us don't really want to spend a lot of time graphing or approximating using Riemann sums. So the goal here is a better way to do this math. And that's where the fundamental theorem of calculus comes in. Here we go. The fundamental theorem of calculus says if we are evaluating an integral from a to b of f prime of x dx, what we can actually do is find the antiderivative f and plug in the upper bound minus the lower bound. So we are going to find, the steps that we're going to take here is we're going to find the antiderivative, or we're going to integrate. And then we're going to plug in top bound minus bottom bound and simplify. So that way the final answer will be a number, a numerical value, the area under the curve. So let's go ahead and look at this example. We are given that f prime of x is 3x squared plus 3, and we're looking to evaluate the integral from 0 to 4 of f prime of x dx. So I'm going to start by just rewriting this, the integral from 0 to 4, and I'm going to plug the function in that we're looking at, 3x squared plus 3 dx. Now, for a moment, I want you to just pretend that there are no numbers on the bounds and find the antiderivative. So what would we do here? Just to review, we would add 1 to this exponent, right? 2 plus 1 is 3, and divide by that exponent. And this other 3 would just get an x. Now, we can't pretend for too long that there weren't actually numbers on those bounds. There were. So we're going to evaluate this from 0 to 4. I'm going to go ahead and identify that that is just going to divide to be 1. So what I'm going to do is I'm going to plug 4 into x cubed plus 3x, and then I'm going to subtract what I get when I plug 0 in. So if I plug 4 in, I'm going to get 4 to the third plus 3 times 4. That's what happens when I plug in the upper bound. When I plug in the lower bound, and I'm always going to subtract here, I get 0 to the third power, which is just 0, plus 3 times 0. This whole thing is going to end up just being minus 0. The red portion, 4 to the third is 64. 3 times 4 is 12. 64 plus 12 is going to give us 76. So I can say that the integral from 0 to 4 of 3x squared plus 3 dx is equal to 76. So there's my final answer. So find the antiderivative, and then plug in the bounds. Plug in the upper bound first, subtract what you get when you plug in the lower bound, and that's going to be the value of the area under the curve without having to sketch a graph of anything. Let's look at a few more examples. Okay, so on number 3 here, again, the very first thing I'm going to do is evaluate the integral. So if I'm integrating 3, that's going to give me 3x plus 2x squared over 2, which is just going to become x squared. And I haven't dealt with the bounds yet, so I'm going to just write the bounds around these little square brackets so that I know I still need to evaluate this from 2 to 5. Then I'm going to first plug in my upper bound, so 3 times 5 plus 5 squared, minus what I get if I plug in my lower bound, 3 times 2 plus 2 squared. And then I'm just going to simplify. 15 plus 25 is going to give me 40, minus 3 times 2 is 6, plus 4 is 10, so 40 minus 10, I guess I didn't need parentheses there. This is going to give me 30. So I can say the integral from 2 to 5 of 3 plus 2x dx is equal to 30. All right, I'm going to encourage you to pause the video and work through number 4 on your own and see how far you get. Then unpause the video and see how you did. So hopefully you had time to work through this. Here's the antiderivative, x to the third over 3 plus x. I'm going to plug 3 in, so I'm going to get 3 to the third over 3 plus 3. That's what happens when I plug in my upper bound, minus when I plug in my lower bound. 1 to the third is still just 1, so 1/3 plus 1. And then I'm just going to go ahead and simplify this. 3 to the third is 27. 27 divided by 3 is 9, plus 3 is 12, minus 1/3 plus 1 is 4/3. So now I just need to simplify this. If I multiply 12 by 3 over 3, I'm going to get 36 over 3 minus 4 over 3. So my final answer is going to be 32 over 3. So the integral from 1 to 3 of x squared plus 1 dx is equal to 32 over 3. Let's do a couple more just to make sure we really have a solid foundation before we move on. Okay. 5 and 6. If you are feeling confident, I really encourage you to pause this video and work through 5 and 6 on your own. I'm going to give you a hint on number 6. You should expand that so that you have a trinomial instead of a binomial squared. Then go ahead and unpause the video and see how you did. So hopefully you've had some time to work through number 5. The antiderivative of sine of x is negative cosine of x. We're going to evaluate that from negative pi over 3 to pi over 3. So I'm looking at negative cosine of pi over 3 when I plug in the upper bound minus negative cosine of negative pi over 3. Now to figure out what those values are, we can look at our unit circle. Pi over 3 is the point 1/2 root 3 over 2, and cosine is the first value. So this is going to end up being 1/2, but this is going to make it negative. Down here, cosine is still 1/2. So I'm going to have minus negative 1/2. So I'm going to end up having negative 1/2 is what that's going to end up being, minus negative 1/2 or plus 1/2, which means that the integral from negative pi over 3 to pi over 3 of sine of x dx is going to equal 0, which does make sense if we think about the symmetry of the graph of cosine. All right, number 6. Let's go ahead and expand and then find the antiderivative. So there are those two steps. We can simplify this to be 12. So I'm going to go ahead and plug in the upper and lower bound. The nice thing about plugging in the lower bound here is it looks like everything's going to be 0. If I plug in 1, I'm going to have 16 over 3 minus 12 plus 9. If I plug in 0, each of these terms is going to be 0. So now I really just need to simplify this, which is going to be 16 over 3. If I combine these, I get negative 3, so minus 9 over 3 is the same thing, which is going to give me 7 over 3. So the integral from 0 to 1 of 4x minus 3 quantity squared dx equals 7 over 3. So now that we've spent some time practicing evaluating a definite integral because there are bounds, we're going to look at what happens if we don't want just the area under the curve as a whole, but we want to know a particular value of a function. And all we have to do to come up with that is look at the fundamental theorem of calculus and just modify a little bit to meet our needs. So what we're going to look at is often referred to as the start plus accumulation method for the fundamental theorem of calculus. But what I want you to see is really all that we're doing when we're looking at this is we're solving for a particular b value. So let's say I knew what f of a was and my goal was to find f of b. Well, I could just take this term and I could add it to the other side, and that would give me this new version of the fundamental theorem of calculus, that f of b is equal to f of a plus the integral from a to b of f prime of x dx. So using this format, and oftentimes you're just going to sort of use this format by accident or by manipulation, can help you find a particular value of a function instead of the entire area that we're looking for. So let's look at an example. If we are given that this is our antiderivative, which should look a little familiar from the front, and we're given an initial condition that f of 0 is 4, and we're being asked to find f of 2. So the first thing I want you to think about is the integral that we're looking at is of 3x squared plus 3. We know what f of 0 is, so I'm going to put that, actually, let's see. We know what f of 0 is, and we want to know what f of 2 is. So those are going to be the two numbers that are on the bounds of my integral. 0 is smaller, so it's going to be on the lower bound. 2 is larger, so it's going to be on the upper bound. And then if we are going from 0 to 2, what that means is this should be equal to f of 2 minus f of 0. We now, based on the first half of this lesson, know how to evaluate this, and we are given what this f of 0 value is, so we should be able to solve for this red value for f of 2. So the very first thing I'm going to encourage you to do is pause the video and evaluate this integral over here, and then unpause the video and see how you did. Just the blue part on the right. So once you completely evaluate the right-hand side, you should get the antiderivative is x cubed plus 3x. You're evaluating that from 0 to 2, so plug in 2, then plug in 0 and subtract. You should get 14. If our goal is to find f of 2, all we really need to do is add f of 0 to the other side. But we know what f of 0 is. F of 0 is 4. What that means is that we can say that f of 2 is equal to 18. So again, instead of finding the full area, the area was 14. We were just being asked for a particular value, and that particular value was 18. Let's do another practice problem. So here we're given that f of 5 is 7, and we're being asked what f of 6 is if we're given that antiderivative. So the very first thing I want you to do is see if you can set this problem up. F of what minus f of what equals the integral from what bound to what bound of what function. So go ahead and pause the video, see if you can set it up. So I want to make sure you can see where each of these values is coming from. We are being given f of 5, and we want to find f of 6. So which of those two values is bigger? 6 is bigger, so that's going to be the upper bound, and that's going to be the first part here. 5 is smaller, so that's going to be the lower bound, and that's going to be the bottom part here. Now I encourage you to pause the video and work through this problem completely on your own. So here I plugged in that f of 5 is 7, and I found the antiderivative, and I plugged in those values. And these numbers are a little large, but I think you can work through this to get to the next step, which should be that f of 6 minus 7 is going to equal 6 to the third is 216 plus 6 squared is 36 minus 12. That whole portion is just going to become 240, and I don't expect that you did it that quickly. This portion over here, 125 plus 25 minus 10 is going to become 140. So if I subtract those, I'm going to end up with 100, and then I'm going to add 7 to both sides. So f of 6 is going to equal 7 plus 100, or 107. So this method, you don't really have to memorize. You don't have to memorize the start plus accumulation format as long as you know what the fundamental theorem of calculus is, because then we can just maneuver it to get to the value that we need. I want to talk about one last topic in this video before we break, and in the next video we'll talk about the second fundamental theorem of calculus. But the very last thing I want to talk about is a unique function and how we integrate with that unique function, and that function is absolute value. If you remember from way back in chapter 1, when we were talking about absolute value, we talked about how an absolute value function can be written as a piecewise function. Absolute value functions are a little odd in the sense that they behave differently whether you're to the left or to the right of the vertex, because remember, an absolute value graph forms a V. So we could really split an absolute value graph up into two pieces where we have one function that is to the left of that vertex and one function that is to the right of that vertex. So this impacts integration because if you think about it, we're talking about area under this curve, which is formed using this green portion of the equation, being added to area under this curve, which needs to use another equation. So the key thing that we need to do is we need to actually split this up into two pieces. We can see very clearly we're talking about two different pieces of area, but in order to do this without graphing the function, which I don't think you want to do, we need to split up our integral at the location that helps us identify this vertex, so to speak. So what we're going to do is we're going to split up our integral at the value that makes the inside of the absolute value equal 0. So if we look at this example here, we're going to split at 0 because that's what makes the inside 0. Now I want you to think about, what is this function doing? If I was to write the absolute value of x as a piecewise function, everywhere to the left of 0 would be the opposite of what's inside. What I mean by that is, if I plug in -5, my final answer would be 5, which means I need to take the opposite of the value that I'm plugging in. If I plug in anything more than 0, I'm going to get the positive value. And if you have forgotten a little bit of this piecewise absolute value relationship, go check out the chapter 1 videos and find the absolute value video. I think that'll help a lot. So what I'm going to do is take this integral from -2 to 3, and I'm going to split it at 0. So I'm going to look at the integral from -2 to 0, and I'm going to look at the integral from 0 to 3, because we have two different pieces of our function that are interpreting that, or that are creating that area. So from 0 to from -2 to 0, I'm going to be using this piece of my function. So I'm going to put -x in here. Now remember, you could actually take the negative out in front of this radical if you would prefer to write it that way. I'm going to just leave it there. That's kind of how I'm used to doing it. But you could take it out and factor it in at the end of the evaluation step. For everything greater than 0, I'm going to use just the function x, so that's going to go here. Now I just have to do the work I've been doing twice. So if I find the antiderivative of -x, that's going to be -x squared over 2. And I'm evaluating that from -2 to 0. I'm going to add what I get over here, which is going to be x squared over 2, and I'm evaluating that from 0 to 3. So if I plug those values in, if I plug in 0 here, 0 squared divided by 2 is still 0. If I plug in -2, -2 squared is -2 squared is 4, then it becomes negative, divided by 2 is -2. So the whole red integral is just going to become +2. And I'm going to add to that what I get when I evaluate this green antiderivative. So if I plug in 3, I get 9 over 2. If I plug in 0, I get 0. So I'm going to add 2 plus 9 over 2, which is going to give me 13 over 2. So I can say the integral from -2 to 3 of the absolute value of x dx is equal to 13 over 2. So the most important thing is that you can recognize where you need to split your integral, and that you can write the negative of the first piece plus the second piece. So go ahead and look at number 10, identify where you need to split it, and see if you can write the two pieces that you need to identify. All right, hopefully you've had time to work at this. I want to know what makes the inside equal 0. That's going to be 0 when x is positive or -1. If you look at this interval, we're only going from 0 to 3, so we don't care about -1. We only care about +1. So we're going to split it at +1. So I'm going to look at the integral from 0 to 1, and then I'm going to look at the integral from 1 to 3. Now I need to figure out what goes where. Well, the second piece is always going to be exactly what we already saw, so x squared minus 1. The first piece is going to be exactly the opposite. If I was writing this as a piecewise function, I'm looking at -x squared plus 1, as long as we are technically between -1 and +1. And I'm looking at x squared minus 1 if we're greater than 1. So I'm going to put the opposite of what I see, so -x squared plus 1. Again, if you wanted these to just be exactly the same, you could have this negative be in front, and then this would still be x squared minus 1. But I'm just not used to doing it that way, so I'm not going to. Go ahead and pause the video and work through this on your own. So we can find that antiderivative, then we can plug in our bounds, and then all we have left is some simplification. So when we combine those, we should get 22 over 3. So the integral from 0 to 3 of the absolute value of x squared minus 1 dx is equal to 22 over 3. So let's recap what we covered in this video. The fundamental theorem of calculus tells us that the area under the curve of the derivative is equal to the upper bound plugged into the original function minus the lower bound plugged into the original function, or f of b minus f of a. This allows us to evaluate a definite integral without having to graph or approximate using a Riemann sum. We also talked about how if we aren't looking for the entire area under the curve, but we're simply looking for a particular value, we can use that value with the fundamental theorem of calculus and manipulate it to get the start plus accumulation method to find a particular value. And then lastly, we talked about how to integrate with absolute value and how you need to split that into two integrals so that you can evaluate each piece of the function or find each area separately. So go ahead and write down any questions that you have. I look forward to supporting you on this. Thanks for listening.